Now, so now we will see how the cost function is actually working. Okay.
Yeah.
Yeah. Is it shared my screen?
Sorry?
Can you see my screen?
Yeah.
Okay. So here you can see what is my hypothesis, what is the parameters, what is cost function, and what is we want. Okay. So our hypothesis is h of theta x is equal to theta naught plus theta 1 x, where theta naught is the bias and theta 1 is the variable which is actually affecting the x. Okay.
Yeah.
So my parameter in this will be our theta naught and theta 1. Okay. And the cost function which we have is the squared mean error. Why it is like squared is because we are taking the square, mean is because we are averaging. So this is called squared mean error. Then my goal is to find that cost function where to find that theta naught and theta 1, which is the unknown variable, that is parameter, for so that my cost function will be minimum.
Yeah.
So like this is a simplified form. So just imagine we don't have any bias. Okay. Assuming that only factor by affected by x, which is affecting x, is just a variable. Okay. It's just simply affecting the x. That's it. So in that case, what will happen? My hypothesis will be changed to theta 1x only.
Okay.
Okay. So now the cost function will be in cost function my h of x will be theta 1x, and so because here we have just only single variable, so we will try to find that theta 1 which will minimize my cost function, which is j of theta 1. Here.
Yeah.
Okay. So if we see here, like if we take like for any, like if we fixed a theta 1 and we made a function h of theta x. Okay. So like if my input is 1, so output will be 1 for this. Like this function is the just linear mx. So input output same value, where I am taking the theta as a single one. Okay.
Yeah.
So if we want to find that like if we want to find error between the error for data points and our cost our predicted function, what will be my error? It will be just I will take the square of differences and I will average it. Okay. So here we can see my difference is 0. Okay. So if that's why my cost function will give me 0 value. Okay. Now if we want to take theta 1 as 0.5. Okay. So what will be the my cost function? Can you tell me?
3.5, right?
Yeah. If my theta 1 is 0.5, so what will be my cost function?
0.5 squared.
My input point is 1, 1, 2, 2, and 3, 3.
So M is 3 basically, right?
Yeah, my M is total number of data points I am taking here is 3, and one data point is 1, 1, where x is 1, y is 1, then another for another x is 2, y is 2, and then third one is x is 3, y is 3.
Yeah.
So Okay. Hello. Okay. The whatever value for cost we will get, it will be not 0. That's for sure. Right? No. So
Yeah.
in this case, my first predicted y1 will be my 0.5. Then the next prediction will be 1. Another prediction will be 1.3. Sorry, just 1 minute. Just 1 minute. Yeah. Then in that case, for each, I am getting some differences, and I will get non-zero cost function. Okay. So now coming to next slide. So here they have written the our approximate cost
excuse
function. Just wait 1 minute. There is some noise from my side.
Yeah, so some background noise.
Yeah. Just 1 minute. Okay. Yeah, it's good now. Is it fine now?
Yeah, it's better.
Yeah. Okay. So where was I? Yeah. So here we can see the cost function is increased if I take the theta as 0.5 instead of 0.5. Okay. So if you plot our parameter and the cost function, here the parameter is theta 1 and my cost function is j of theta 1. So we saw for two values. So in case of theta 1 it was j was 0, and for theta 0.5 I am having j something 0.58. You can on the right section of the screen you can see the plot between j of theta and theta.
Wait, why are there 3 points? 0.5 minus 1 plus 1 minus 2 plus 1.5. Oh, okay.
It's just a plot showing that because I can take any theta. Okay, I can take theta, like that is my parameter. So I can take any value. It can go from positive to negative. Okay, like it will be just I will be for every theta I will be having different function. Like
Okay,
if
so,
theta
so
as
theta is your repeated variable.
what pardon?
Theta is your repeated variable. Like, what is the 0.5 significance?
See, like I had these points. Okay, just 1 minute. Okay, just say some data like this. Okay, 1, 2, 2. This data I am having. In what we do in machine learning or till now, what in linear regression, I wanted to find a function that is hypothesis which will accurately tell my data points which I am having now. Correct?
Yeah.
So here I am having 3 data points. One as 1.1. This is my x. This is my y. Okay. Then other data point is 2, 2, and third one is 3, 3. Okay. Like here we can see from the from the plot only we can tell that my best line will be this line. But how a computer will know? For that only we said, okay, this plot, this data points can be plotted, can be mapped by h is equal to some theta and x.
Hmm.
Okay, so my computer doesn't know whether this is this line or this line or this line.
Hmm.
How computer finds which one is best line? Through the cost function, through the differences it's getting from each line. Correct?
Hmm. Yeah.
So here my j is the cost function. J of theta is the cost function. Okay.
Yeah.
This is actually the y bar prediction. Actually theta of x. Actual format.
Yeah.
We can just simplicity. Sometimes we will use y bar for the predicted value.
Yeah.
Okay. So and how we find j of theta? My j of theta is 1 upon 2m. So my m is 3 here. So 2, 3. Okay.
Yeah.
Into summation of like if yi minus yi. This where I will be 1 to 3. Clear?
Hmm.
Okay. I will use this only. So like if I plot, you know that my goal is to minimize j of theta, and the variable which I am having my machine learning algorithm, my system doesn't know is theta, which theta will be best. So what we are trying to do, we are finding that theta which will minimize my cost. So if I plot graph between theta and j, okay, so we saw that at 1 j was 0, then on 0.5 it was giving some point, it was something 0.58. Okay.
Yeah.
So similarly, if I am taking something, some other value, it will be something else, some okay, it will be something like this. If I am
Yeah.
taking theta some different values, so I will be getting some different value for j. Okay. So actual plot which we will get like at one point I will get 0, and for all the other points I will be getting some other values. Okay.
Yeah.
And if I know with cost function my theta is varying like this, so then in that case I can tell this is my best value, this is my best value for theta, and I should take my equation as y
Yeah.
bar equal to
What?
1 into x, which
Yeah.
one will be y bar is equal to x. This is my best curve for given data points which we discussed just now. Okay,
Oh, okay.
is it clear, or you want me little to explain?
And I think I got it now. Yeah.
Got it? Yeah, great. So same thing we are doing it here, like we are on for theta plotted, then again with different theta we plotted that value. Okay, so
Yeah.
in this way we were getting plot like this, the bowl shape. Okay, this we call the bowl shape of plot. And my best theta, from this we get to know that my best theta is the where my cost is 0, it is theta 1. Theta 1 is equal to 1. This is my best theta. Okay,
Okay.
clear?
Yeah.
Huh. So till now we discussed here we are discussing what with one variable. Now if we want to see more about that cost function in coming slides, then you will understand how it's coming and going. Okay. So this you know what is my hypothesis, my parameter, then my cost function, and my goal. Goal is to minimize the cost function for given parameters.
Yeah.
Okay. So in this case, I am taking bias also. Like before, we just only took the slope of the just one variable, which was one parameter, which was actually affecting my x. Now here we are taking something constant also along with that parameter, which is my theta naught, which this we every time we will use as a bias term. Okay. So here we want to find both bias value and my theta 1 value.
Yeah.
Okay. So like now we have two different two variables, and based on the two variables we are finding cost, how it is varying. So this is actually that this counter plots, like this balls a 3D plot. Okay, so in one axis this is one axis is telling me theta 0, another one is theta 1, and then the cost function, how it is varying. So did you understand this graph from the one, like before we used it for one variable only, that's why it was just 2D graph. Now we are showing for two variables, so it will give me 3D graph.
Yeah.
So what we want, like we want that theta 1 and theta naught where my cost is minimum. So you can see like lower part is blue color. Okay, blue color is area where I am getting the minimum cost function, minimum cost value. Okay.
Yeah.
So to simplify this, we will use the counter figures. Okay. I will tell you how this is coming. So my cost and theta function was like this curve, this ball shape. Okay. Now because it is the in three dimensions. So how it will be? It will be in one more axis. Okay. So just take different color. So it will something on just overlapping on some different. This is the outer plane, Z plane. Okay. It will be like that. Huh.
Yeah.
So now if you flatten that plane, so how it will be? It will look like something ellipse.
If you do what?
It will be if you flatten that ball shape, 3D ball shape, it will look like this.
Flatten? What do you mean flatten?
Flatten means making that ball shape from 3D to 2D.
Okay, I have a ball. I have a ball. Let me say I am a lemon. I want to squeeze it. When I squeeze it, what it will become? From spherical to it will become a plane, right?
Yeah.
So that is for seasoning.
Okay.
Like
let's squeeze it.
So what we are doing from the 3D, we are making it to 2D for like for the simplicity of understanding. Okay, so just imagine this is on like these are the this is balls, and it is showing me the 3D architecture on 2D plane.
Okay, so let me ask. So what are you able to understand, Amal? What she is trying to explain?
Okay. She's
okay. So let me put it in this simple way. Have you heard about contours?
Contours. I heard about it.
Okay, so contours are those graphs or those plots which tries to identify the density of the height. Right. So if you see when you are trying to play some aeroplane simulator games, that will be giving in the radar map red color, yellow color, blue color, green color, right?
Yeah.
The mountains. So those are known as contours. Okay. So here also this whole diagram, all the two black, two red, two yellow, all are in a three-dimensional hemispherical way, right?
Yeah.
Now you have a hemispherical. When you sidewise you look, it will look like a hemisphere. Now directly go to the top. Okay. From the top you look. So these are like the bowls, and these circles are the top figures, right?
Oh, the top figures. Okay.
Yes, top figures. So these are the top figures. right? How it will look, right, Arpana? Am I correct? That is what you want to mean.
Yeah, the outer one is the outer part of the hemisphere.
Yes, the top part.
This one. This is the outer part of hemisphere. Then I'm coming to inner part. Then most, and then this will become the core, like the lower point of hemisphere.
Yeah.
Okay. Okay. So, like you understood that this is my the yellow part. This one is my core part of the hemisphere or ball. Okay. So, like if you take any theta 1, theta 2, and here is j. So if you take some theta naught is equal to some 2 value and theta 1 is equal to 1. So what will happen here? Like it will give me some cost value. Something. Just imagine if I am getting this cost value. Okay. What I will do now? I will try to go to that point where I am having the minimum cost value. So I will see, okay, inside I am getting some low value. So next, if I change the theta, I can go here like this. So my main aim is to find this one. This is my lowest point where I am getting the minimum cost function. Okay.
Yeah. Okay.
Yeah. So you can see like here he is showing some for different theta one and different cost value he is like we are getting, and our goal is to go in the core part of our my contour, my ball. Okay. The center J. This is what I required. Okay, the minimum cost value. So, they give an example. If I'm having some function with hx is equal to 360 into 0. Like if I'm taking the theta as 0, so my output will be predicted value will be 360, and for that they have given this is the cost. Okay.
Okay.
Like this red mark is the cost for particular theta naught and theta 1. Then similarly, like if I am taking some other value, so that will be my different. Like here the hx is different from the above one, from this horizontal line. This is with some slope, so it will be giving me some different cost value. Okay.
Okay.
Like similarly, like this one was the line which was giving me almost minimum cost. Like here you can see for this particular theta naught and theta 1, they are getting the point at the center, almost center of the ellipse. This is called the ellipse. Okay.
Yeah.
So in this case we can say the particular theta naught and theta 1 is the actual theta naught and theta 1 which we should use to get the minimum cost value. It's not necessary that the cost will be always 0. It's like sometimes it can be that we won't be able to find that exact function which will give me 0 cost value with simple line. So in that case, we actually go for the higher function. Okay, so that depends upon the different algorithm and all. Okay.
Yes.
So.
Arpana, just wait. Arpana, just wait. Aman, you want to continue now, or shall we have some break, like after some time or some hours or something? We'll do it.
No, we can continue.
Okay.
Yeah, it's like we are already in flow, so it's better.
Okay.
Yeah. So how we should propagate, how we should find my theta 1 and theta 2 to get the minimum cost value. But to make this happen on the system, okay, we use an algorithm called gradient descent.
One sec.
Like you understood that this is my cost function, like cost and relation with cost and my parameter theta naught and theta 1. So you know, okay, I should take the minimum, the center of the core of my this plot, but how a system will understand? He has to take that particular theta one. Okay,
Yeah. Wait. 1 second. I'll just use the washroom and come.
okay, no problem.
Hello.
Yeah, hello.
Yes, sir. I'm back.
Yeah, we will continue. So you understood how we should find theta 1 and theta naught and theta 1, and to make this happen on the system, we use this gradient descent, okay, gradient descent function or gradient descent algorithm methods actually, okay.
Yeah.
So now we will see this method. This, you know, we have the cost, we have the function which is cost function, and what we want to find that minimum theta naught and theta 1, which will we want to find that theta naught and theta 1 which will give me the minimum value for j of theta naught theta 1. Okay.
Yeah.
So we will start with some random value because we don't know exact value. Just as a random guess, we will write some theta naught and theta 1, and then we will decrease it. We will decrease so that my cost function should decrease. We will change this to some value, and what I want that my cost function will decrease. So at one point of time, by changing, we will get the minimum cost value.
Yeah.
Okay, so this is what we will make system to do. This is that 3D plot, like how we are going. So I will tell you how it's happening. What I said, first we will take some random theta naught and theta 1. Okay. So the first point here near the red, we just assume we take that theta 1 and theta naught, so it gave me particular j value. Okay.
Yeah.
So this is what this is actually the hill and valley. Okay. So you are at some point of hill and you want to go to the lowest valley, correct?
Yeah.
So what you will see, you will see your surrounding, and you will see, okay, that is the lowest point you can see, so you will try to go in that particular direction. So
Yeah.
he came to the next point. Okay, then from next point again he saw what is how should I go. He then come to the third point. So in this way you can reach the lowest point which is visible to you.
Yeah.
So that is the blue point, like the last end of path, this blue one, that is lowest you can come. if you start from this particular red point, which is the particular point in the hill,
Wait, but how will you know which is the red?
huh?
Uh, how,
Uh,
how how will you know which is the red point? If
we
into
actually
the
don't
bottom
know.
one.
We actually don't know. Like it's what you can assume. Like your with theta 1 and theta naught, your cost is coming up, coming down. It will be something like that, which is
Oh, then you follow the direction that's going down, and then you. Okay.
that I will tell. So it's just a similar to hill and valley.
Yeah.
Okay, so you are at particular point of hill. You want to go to the valley, the lowest point of that place. So you will say where you can, how which direction you should go so that you will reach.
Yes.
Okay, so here at one point you will stand and you will say from which coordinate I will go. So here just take coordinate as theta 1 and theta naught. So you will see, okay, in this particular north direction, I will go I can go low. So you took some other theta 1 and theta naught, other the coordinates, latitude and longitude. Okay. So this again and again you do. You stand, you come to the next point and you see which direction I should go so that I will reach that minimum point. You go to next point. Again you see which latitude longitude I should go so that I can reach the minimum point.
Yeah.
Okay, so this is a gradual process and we do until we reach the minimum point.
So it's more like trial and error, right?
Not it is like optimized way of doing this. Instead of just trying any random point, here we see particular direction how we should go.
Okay.
Instead of going just any direction, any north or south, we see actually which is leading me to the lowest point, and that particular direction I am going.
Correct. Yeah.
Okay. Yeah. So this is the another example. Like if you are at some other point, like if you initially only if you start with some other point, other coordinates. So this can lead to you some different lower point.
Yeah.
If you are at hilly place, okay. So for hilly place, there will be some near lowest point, then something will be complete lowest point for complete some 100 square meter. If you are in mountain and mountain is spread on over the thousands of square feet. So there can be some other low minimum point, and in complete 1,000 square feet, it can be something else minimum. Agree?
Yeah.
And depending upon which point actually you are at the mountain, because you can see only the nearby places. You can't see the complete mountains. You can just see nearby places. So in among nearby only you are seeing which direction you should go, which will lead to you the nearest lowest point which is visible to you. Okay, so that's why if you are depending upon where you start, you can lead to different minimum values, and this is the concept of local minima and local and global minima.
Yeah.
You know local minima and global minima term.
Yeah.
Okay, so I think this would be clear now for you.
But then
Yeah, say.
Since there are many blue valleys, how can you find the lowest cost, like lowest value?
Yeah, that's what I'm saying. Right now, mathematically, we will just decrease it so that we should get the minimum value. Okay, this is just for the like visual. Mathematically, we will write equation to do the same thing, but this is the concept which we use in our gradient descent. Like this concept is used like going towards the lower value, lower where my cost is lower, is the what gradient descent will do.
okay.
Okay.
Yeah.
Yeah. So gradient descent okay, like if just tell me how you will find which is the lower point. If you are at hill, how you will say that this in this way I can go to the lower point.
As the points increase, like for us, one increases the cost will be decreased, and you know that approaching a valley. Right?
Yeah, just assume that you are at this hill. Okay, you are at hill. Okay, this is you are at hill. Then there is some valley. It is something like this, hill and valley. Okay,
Yeah.
it is something like this. So, and you are at point. You are at this point. Randomly, you came from airplane. They dropped you, and you reached here.
Yeah.
Okay, and so if you are here and you can see for you what you can see is like for you the minimum value is this point. This particular one is the minimum for you. Like you just see the visible area. You see that this is the minimum point. So you will think you should go in this direction. Your main goal is to reach here.
Yeah.
Okay, now if you can say that whether you should go this way or this way.
Oh, then okay. Then you decide based on you can see the increase in view.
So what is this? This is actually the slope. Whether
Yeah.
it is increasing slope and decreasing slope, which is in mathematical term, this is the gradient.
Yeah.
Okay, and we go toward where my gradient is decreasing.
Yeah.
That's why we call it gradient descent. Okay.
Okay. Yes.
See, you have to go to the lower point. You are
Yeah.
in this particular location. You will see whether to go up or down. So you will see, okay, down means slow. Your slope is down. That's why you are saying down. Otherwise, if something is planar area, if you are at plateau, okay. So can you tell anything from here with slope and down? This is plain for you. Okay. At this point, you have something coming lower and going up. So you can say on the basis of slope only, you say whether it is up or down.
Yeah. Okay.
Yeah, which is in mathematical term, which is a gradient.
Yeah.
Okay. Yeah. So gradient is taking the derivative of cost function.
Yeah.
Because we want to minimize the cost function, we made hill based on the value of cost function. So my gradient will be derivative of cost function. So this is the equation for that. Okay, top left corner. You can see your theta has to decrease by the gradient of cost function with respect to theta. Actually, what you are doing here, you are decreasing that theta parameter with your decreasing slope.
Okay.
Whatever slope you have, with that you are decreasing your theta value.
Yeah.
Okay. So the equation which comes is for gradient descent, like we have to decrease the theta so that my gradient will decrease. I have to go in that direction. That's why we write theta is equal to the previous theta minus alpha. Alpha is the learning rate. How much step you should take, whether you should take step of 1 meter or 2 meter. Like in walking sense, whether you should take some centimeter step or 1 meter step. So that is what alpha is doing here. Okay.
Wait, what do you mean? Like,
See, if you are at hill and if you are walking, Okay, so if you are going down, so that you will take step only, like we will in going down, we will while walking we take step. So sometimes some people take bigger step, some take smaller step.
But is this the gradient of?
Huh?
Is alpha the gradient of that?
Alpha is that whether you should take bigger step or lower step, and this is called the learning rate.
Okay,
At
okay.
what rate your gradient should go, and your gradient is derivative of cost function, that is delta of j theta naught theta 1 with respect to theta. Here it
Okay.
is like this one. This is, so your theta 1 will be, we will assign in theta 1 minus alpha gradient of cost my theta 0 and theta 1. Okay, theta 1, and how my theta naught will update?
Wait, what is that before J?
Huh?
What is that before J?
This is alpha, learning rate.
No, after alpha.
This is okay, wait, just I will tell you. Let me just write it.
Oh, derivative. Okay.
Yeah, this is derivative. You know partial derivative?
Yeah.
Yeah, so here we are doing that partial derivative. Like if we are finding with respect to theta, we are assuming my theta 0 as constant value. So we are just taking the derivative with respect to theta 1.
Okay.
Yeah. And here we are making this constant, and when we are taking with theta naught, so in that case we make theta 1 as constant and we do the partial derivative.
Yeah.
Okay, which is my gradient.
Okay.
So this is the, we have to update both theta naught and theta 1. So what we do, like first we will find the how much theta naught you should update, then how much theta 1 you should update, and then you change the theta naught and theta 1 value. Okay?
Yeah.
Okay, just tell me why this is incorrect. The other one, right section, why this is incorrect.
10.1 is
Any guesses, anything?
because I'm not sure. Is it because of that arrow markers? Because theta 1 is supposed to come first.
Yeah, you are getting somewhat correct. Yeah, see, what we want to do when we take a gradient, okay,
Yeah.
then we want to update both theta 1 and theta naught. Like what we do here, we want to update both theta 1 and theta naught. Okay, so if I'm taking like at iteration means doing something again and again. So if I'm starting with I at I is equal to 0, if I'm taking some theta 1 and theta naught something, some 0, 0, just simplicity, just take 0, 0. Okay, so based on 0, 0, we have to update first theta. You can update anyone, either theta 1 first or theta 2 first, but you have to first update both of them, and then you have to change it.
Okay.
Otherwise, what happened, like here you calculated this delta of this value, you calculated it. Okay, partial derivative for at theta is equal to 0, 1, 0, 0. Okay, then you updated, so let's assume it you got this as 1, this also as 1. Okay,
Okay.
now what you will do, in I is equal to this is your I is equal to 1. So at I is equal to 2, just sorry. No. At I is equal to 2, now you have theta naught and theta 1 as 1, 1.
Yeah.
So again, you should do this. You should update both of theta naught and theta 1 for 1, 1. Okay, you can't mix, like you can't do like this, that you first updated this theta 1, then again you are changing this value theta 1, and then you are calculating this. In that case, it won't be the original, it will be the updated one. Not will the, it won't be the at I is equal to 1. This theta 1 value is I 2. Are you getting me? Okay, wait, I will just clear this little. So, okay. So, see, at I is equal to 1, you have theta naught and theta 1, 0, 0. Okay?
Yes.
Now, you find derivative of j with respect to theta naught. Okay, at I, at I1.
Okay.
Then again, you updated theta naught. Now at I is equal to 1 only, you have to update theta 1 also.
Okay.
For integration, we have to update both. So, and if we are doing it continuous, like 1 by 1, so at this point we have this will be based on 0, 0 value of theta naught and theta 1.
Yeah.
Okay, and just imagine at this point we have updated value and we are getting 1, 1. For theta naught and theta 1 we are getting 1 and 1. Now your next iteration will come I is equal to 2. So,
Yeah.
you will find both j of theta naught and j of theta 1. Okay.
Yeah.
Now just assume I is equal to 0, your theta naught, theta 1 is equal to 0, 0. You updated theta naught and it gave you 1. Okay.
Okay.
Now, if then you are updating theta 1, so for that you will, if you are finding del of j with theta naught is equal to 1 and theta 1 is equal to 0, so it is wrong actually.
Yeah.
Where is my drawing gone? Just 1 minute, I just missed it. So now, actually, what you wanted to do, you wanted to update this with theta is equal to 0 only. Not this one, but with 0. But if you are not doing it simultaneously, like if you are doing updating this one and then calculating this, so here at this point, your this value will be 1, which is wrong.
Okay.
Like if you're not getting, I will take some other example or something. Just
All
let got na? That's why only we use this process, this left hand side process, not the right one. Otherwise, this theta naught at that place is the updated one, not the previous one. It's updated. So this is the wrong. Okay. Yes. So coming to the next slide. So you understood, in the gradient descent algorithm, what we do, we go towards my gradient is decreasing.
Yeah.
Okay, and in this we take the learning rate, which tells me how much with how much weightage I have to go the gradient. So alpha is your learning rate, and this is the derivative del of j theta 1 theta. Okay.
Yeah.
Yeah. So this is that only they are telling, like I have to go toward the negative slope, and like my alpha is the steps which I have to take. Yeah. So now we will see how alpha is affecting. Okay.
Yeah.
So this you understood. Like if you understood, like the cost function will be of the plot between theta and cost will be of bowl shape.
Yeah.
This is theta and this is cost, so it will be some bowl shape. Okay.
Okay.
Now how I am, like if I am at this point, so I want to go in lower direction. Okay. So if I am taking smaller step, my alpha was the parameter which was telling me how much step I should take towards the gradient. So if I am taking this low, if I first I took this step, I reached here, then I took this step, then I reached here. Similarly, I reached here, and again if I go this much step, so I will come to this point, the lowest minimum value of j. Okay.
Okay.
Now assume if you are, like we started with this point. Okay. Now if you started to, you thought that by taking the largest step you can go early, you can reach your minimum value early. So let's take the largest step. We reached here, we came here, now you are here, you missed it, you are here again. You will take something like this, then this, it will be like you will be lost in that bowl, that cost function space. Okay. So this is what happens if you take the very large step, but if you take sufficient step, like sufficient size step, so you will reach in proper time. Like it's not necessary to take only this much step. Okay, you can take this much step, but yeah, you should not take this much big step. That's the main point of using the alpha in our gradient descent function. Okay.
Okay. Yeah.
So this is what they are telling here. Like if they are taking the small step and if they are taking the big step, then you will be lost and you won't be converging. Coming to the lowest point is called as convergence. And if you are taking the biggest step, so you won't converge. So that's why we take the
What's the effort?
medium value for the alpha, not too small, not too big. Yeah, this is the I was telling you that the local that we have to if we see the local minima for us. Okay.
Yeah.
Yeah, so this is telling about like this, and in this graph if you see, this is the local optima, and another the deep, right left side one is the global one.
Okay.
Okay, so for this also, like to get the global one also, that concept will come, but somewhat later. Okay, that I will explain properly in later stage of the learning. Okay, this is the same thing, like the steps, like how much step and what to take. Okay. Now how we use this with linear regression. Okay, now you studied the concept of gradient descent. So is it clear?
Yeah.
So now we will see it with the linear regression, how it works with the linear regression. Okay, so our equation will be same for gradient descent. The equation will be same as theta of j is equal to previous theta j minus alpha into the gradient. Okay, and then my linear regression model, there we have the j as mean squared error. So, if you take the derivative of theta, so what will will come down, okay, and inside
You're not very audible.
hello,
There's some background noise.
just I think it's from someone else side. Nimai sir, hello. Wait, let me confirm with him. I think it's from his side. Nimai sir? Just 1 minute. Hello, Nimai sir. Please mute from your side.
Okay, okay.
Yeah, it's good now.
Yeah.
Hello, Aman. Yeah.
Yeah.
So what the like if you take the derivative of this, what you will get? You will like 2 will come, and then it will be like just 1 upon m summation of h of x minus y into x. You got this derivative?
Wait 1 sec.
Just read it once.
How is it 1 by m in this case?
Yeah, I will tell you. Stop it, another time. Our equation is j is equal to 1 upon 2m summation of h of x minus y square.
Right.
Clear? So now how we can write this? That is equal to 2m. If you take this like if you expand inside summation, so our x is theta naught plus theta 1 x minus y
Yes.
whole square. Okay, so in what like this is equivalent to, if you say some constant value c, okay, summation of z square, it is something similar to this.
Yeah.
Okay, so what will happen? Oh, sorry. So what will happen if we want to derivate some c summation of z square, okay, with respect to, here we wanted to derive it with theta, which is z is of in term of theta. So what will happen? Your c will come out because this is the constant value.
Yeah.
Then summation will be as it is, and your j, because j is squared, so one j will come outside, and it will be derivative of z. This will become under whole summation, derivative of z upon d theta.
Wait, what is that?
And z is just similar, like instead of writing this complete one, we are using z.
Okay.
Okay, so now it became, wait, so it will be, c will be come out, c will come outside, it will be summation, okay, and because this is z square, so z, you can take z also outside, like if we take inside only, no problem. So it will be derivative of dz upon d theta. It will say similar to this, like it will be this one.
Yes.
Okay, same thing is used there. Okay, so like this c is that value which is like 2m. We are taking that 2m, and I missed one thing. Your, because this is square, your 2 will come out. Like it will be 2 of z. Yeah, okay, and because if you replace this c with 1 upon 2m, so your 2 and 2 will cancel out.
Oh, okay. Yeah.
Okay, so now what you will have? You will have z upon, you will have z upon m summation of this function.
Yeah.
Like, because my z is inside summation, so it will be inside summation only. Like it will be, sorry, it will be z and 1 upon m.
Yeah.
Okay? Yeah. So same thing is done there. Like this is the how we are getting m. Understood?
Yeah.
Okay. So here we you can see one is with respect to theta naught and another is with respect to theta 1.
Yeah.
Okay. So, and what we do, we just update the gradient value. So if you replace this gradient part, so it will become this equation, theta naught is equal to theta naught minus alpha 1 upon m, then that complete the gradient part will come.
Yeah.
One is for theta naught and then other is for theta 1. One difference which you can see, like in case of theta naught, the x term is gone. Because theta naught is only at this place, so it will, the derivative will be just simple 1. But in case of theta 1, the x will be there because that's not constant value, that's the variable term for theta 1.
Yeah.
Okay? Yeah. So you understood this equation, what we have to do?
Yeah.
Okay, nice. So yeah, this is the same slide. Like if we are coming to one point, so we will reach the minimum value based on different from the different locations we start.
Yeah.
Okay, like here 2 minima was there, so if we start from this point we can reach there. If we start from other point we can reach till there, till other minima. Like same thing, we reached, if we started from different point we reach different minima.
Yeah.
So yeah, this is actually this ball shape, this is actually the convex function. There is like different definition of convex, like which function can be convex function. I won't go in that detail now. Okay, but if you are interested, let me know, I will send you the doc for that. Okay.
Okay.
Yeah, so this is the same thing explanation, like this is like similarly as we use the gradient descent separately, so in same way this is applied with the linear regression also. Like it just the in now we have the particular cost function, which is a particular differentiation of the cost function. Okay, so for theta 1 the partial derivative, and then again for theta 2 partial derivative and updation according to that. So same thing is explained here. Like this is how we start from one point and we try to reach till the, with descent we reach till the minimum point. Okay.
Okay.
Like explanation of same thing, like after one iteration. So yeah, so with taking theta at the center of the ellipse, that counter plot, so the yeah, so the where we are getting the minimum cost value, this was the function which they got. So here you can see this is like the very best suited line to, yeah, so for the data, which is the best fit line.
Okay.
Okay.
Yeah.
So now what we do, okay, what is like the batch gradient? So what happened, like if we go for like what you have seen, like we were summing it from I is equal to 1 to m. Okay, so what is that? We are taking that complete data set, we are finding its cost, then we are updating it. Okay, so this is called the batch gradient descent, because we are taking the complete batch of the data and then we are using it our gradient updation rule. Okay.
Oh, yeah.
Yeah, this is called the batch gradient, and this is the end of this slides. So you have any doubt in the gradient descent?
I think
Just this one, batch gradient descent. Just I'm a bit confused. Batch gradient descent.
Okay, I will tell you. Yeah, so we started with using linear gradient descent with linear regression. So here you see that we are finding this cost function for each data point. We were not doing just we were not doing like we are just taking a single data point, then we are finding the gradient, then we are updating it. We are not doing this. The summation from I is equal to 1 to m is telling me that we are finding the cost function for each data point for a single theta naught and theta 1.
yeah.
And then we are updating that theta naught and theta 1, and again in next iteration what we are doing again same thing, we are summing, we are finding the cost function for all the data points and we are updating the theta naught and theta 1. This one, like here the summation 1 to m means that we are taking the complete data points for each iteration.
Yeah.
Yeah, so actually like if we are taking complete data points for our updation, so in that case we say it as a batch gradient because we are taking complete batch of data. Okay, actually like you can also do, you can just take a single data point, so in that case there your summation will go and then you can update, but that's very slow process. So we actually in practical we don't use completely batch, also not completely single one. Okay, like we take some data point and then we update, and that these all things we will see in coming lectures, so not a problem. So this is actually what batch means.
Okay.
Okay, I will go through the slides. Just let me know if there is any doubt, because this should be very clear. Yeah, we started with this slide. I will just pause for a second. let me know if you want me to stop at any slide. Okay.
Okay. Wait. One sec.
Yeah, sure.
So this y and x, like that, can you just scroll up like the previous slide?
Hmm?
That h naught x and the other x, that's basically x1 and x2.
Where h naught x?
So these are the two changing variables, like basically price and square feet, right?
Yeah. This is equivalent to that only.
Okay, and then from that we have theta naught and theta 1. Theta 1 is
Yeah.
the gradient and theta naught is the bias.
Yes.
Okay, yeah, got that. Okay.
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 Yeah. Clear?
Yeah, and then the cost function, that h naught xi minus. Okay, that's from the actual point. Goal is
Yeah.
to minimize that. Okay.
Okay.
Then from that we have that valleys and stuff like that. Okay.
Yeah. From this it will start like first one.
Yeah.
Okay.
Yeah. So when where theta 1 is that's the minimum point of that parabola, that is the lowest cost, and that is the gradient, the best fit for the h naught x and x, right?
Yeah. That taking theta 1 was the best for particular data points. Given these 3 data points, it is the best.
Okay. Yeah. Okay. Then contour plots. Okay. Yeah.
It's just try to assume, like if you try to, for simplicity, we make contour plots to represent it. So you can see the blue part and then red part that are the with lower higher value. So you can see in contour the red are the outer ones. Okay.
Yeah. All right.
Then here we are on gradient descent, and you understood why this is correct and why the right one is incorrect.
Yeah, that's because we didn't change the theta 1, right? We only changed theta naught.
Yeah, correct.
Okay, and wait one sec. Okay. Okay. Yes.
Correct. Got it.
Yeah. Yeah. Got it.
Then the gradient descent.
Yeah.
There's steps for the like learning rate.
Yeah, and
Yeah,
learning rate
this is
value.
new.
Yeah.
Yeah. Then again applying gradient descent will algorithm.
Yeah.
So this is calculation in linear regression for the gradient.
Wait, this one. Yeah, this one I think I had a bit of an issue. Linear. How is it linear regression and all?
See, for linear regression, our what is our cost gradient? In
Yeah.
gradient descent, you understood like we change our parameter with gradient. Okay. So
Yeah.
because in linear regression, the cost function which we are taking is this 1 upon 2m summation of hx minus y whole square. So
Yeah.
if we take the differentiation of that with respect to theta naught and then with theta 1, so we will find this value.
Okay. Yeah.
Okay, and that thing we replaced it in actual gradient descent equation. So and that is like in actual gradient descent equation, we are replacing our cost derivative in order to get this equation.
Okay. Oh.
Or any doubt?
No. So this one is just writing theta naught and on theta 1 in terms of j and all, right?
Yeah, this is writing in term of j, like complete equation which we will use in our code. Like while coding, we will use this equation to update our algorithm.
This allows you to compare theta naught and j, or theta 1 and j, like two variables instead
Yeah,
of
like because here we are taking just theta naught and theta 1. That's why we wrote for theta naught and theta 1. If we have many other theta also, like other parameter also, then we also, like how many parameters we have to update them all.
yeah.
Okay, like just see, this is for like if we tell the actual algorithm. Okay, actual gradient descent algorithm is your this value. So in this, if we are doing it with linear regression, then we will write that we are writing the derivative of linear regression, which is my derivative of cost function, this one.
Yeah.
Clear?
Yeah.
Okay. Even if after the class, if you have any doubt, you just write us. Okay.
Okay.
And if you feel anytime that we can do this fast or we have to go little slow, let us know.